I'd like to introduce Jason Condon, who's presenting today's webinar, Explaining Soil Testing Jargon. Jason is Associate Professor in Soil Science at Sturt University in Wagga and is part of the New South Wales DPI Soils Unit as well. Jason's taught soil science at CSU since 1996. He has a PhD in nitrogen cycling and certification and continues to research strategies to optimise management of soil acidity in collaboration with New South Wales DPI and local farming systems groups. Jason also leads ACR-funded farming systems projects in Vietnam and also provides soil advice and support to local advisors and grower groups in Australia. And it's a great pleasure to hand over to you now, Jason.
Hello, everyone. What I thought I'd do is not do PowerPoint. And so we've gone to analog PowerPoint. So you'll see my hands and you'll see pens, and that's the way we're going to do it. Some of the stuff, like you'll know, some of you would have learned at uni if you've been there, but I reckon some of the things, even if you pick up just a different way to explain it to a client or a colleague, that would be useful. But I know when I teach this stuff, it's amazing how much is done in practice just because that's how it's done without actually thinking about what's happening. And so we'll delve into that a little bit, understanding that I'm as guilty as anyone falling into that trap as well. So no fingers of blame pointed. But today what I wanted to just talk about is why test in the first place. Going to hit some basic soil components that are really foundational knowledge to the soil test itself, soil test results, and then understanding what's on the test report. So that's what we're going to hit. So starting off just with why test. So I reckon there's largely two reasons. One is to monitor the soil condition that is the impact of our management. And for that, you know, the standard sort of 0 to 10 soil sampling probably does a reasonable job of that, basically looking at things like, you know, it might be pH or Colwell P or available P through time. And so, you know, if we soil sample every 3 years and we can see things doing this, then we know, you know, we've had some good years and we've dropped it to here. Now we need to do something to get it back up to here. And you know, if it's a pH effect, you know, you put 2 tons of lime on, what was the result of that? Did we end up here or did we end up here? You'll only know if you test, right? So there's that sort of monitoring. And the other reason is to diagnose. And so, you know, there's a problem there, and it might be, you know, often, you know, it might be a comparison within a paddock. This, you know, within this paddock, there's some good bits here, but over here is really bad. So why is that? So we can soil test in both and compare. So that's useful. Or it might be between paddocks, or it might be, you know, we've had some, you know, excellent rainfall. There's water in the profile, but my yields still suck. So what's the limitation? Like, can we look at the soil test to find out what the problem might be? And for that, I reckon a lot of the time that 0 to 10 sampling doesn't pick up the soil constraint. Often the soil constraints are happening in the subsoil. So if you go looking, if our go-to is the 0 to 10 to diagnose problems, we'll probably miss them 80% of the time, I reckon. That impacts what samples you take, what depth of sample you take, and it will also impact what you get tested. Another example of that, monitoring through time now, topical, is soil carbon. Like, people are looking at that to track changes through time, and that might be at a point within a paddock, you know, so a monitoring point that's sampled intensively through time so that we can check carbon changes in that particular area. So let's go and look at these basic soil components that matter in the soil test. Now, there's lots of stuff in soils, but I just want to talk about where the action is, and that's in the clay. And so you will probably know that in clays, you can have layer silicates, you can have sesquioxides, and there's even some organic matter can fit into clays if we're calling clays anything that's less than 2 micron in diameter. Now, these layer silicates, I represent, when I draw clays, I always draw them as a circle, right? Like a particle. But these layer silicates are super, super small, the actual layers themselves. And so these particles of clay are actually made up of crap loads of these layers join together to form particles. Now, inside these layers, largely they're made up of aluminium oxides and hydroxides and silica oxides and hydroxides. You end up with negative charges being created at soil formation. So these layer silicate clays actually have a permanent negative charge. And because they have a negative charge, positively charged things in the soil solution will stick to them. So we can have cations, which I just draw as circles with pluses on them, so they're positively charged. And I remember that because when you write cation, it has a positive charge in it. And so opposites attractors, this is just electrostatic force of attraction. And so cations will stick to the outside of a layer silicate. And here's the go. Every negative charge in here will have a cation or a positive charge satisfying it. So if you've got two negative charges here, you could have a cation with two positive charges satisfying these two negative charges. But whatever negative charge this clay has, it will have a corresponding number of positive charge cations satisfying that negative charge. Okay, so this thing is permanent, always negative, doesn't matter what you do to it. If you can heat it up, you can cool it, drop it in acid, whatever you like, take it out, get it drunk, it will always be negative. Can't change that. For as long as that thing is a clay particle, it will have its negative charge. Now, not all layer silicates are equal. There are some, and we call them 1-to-1, and that just means they've got one layer of silica oxide and one layer of aluminium oxide. And then there are 2-to-1s, which have two layers of silicon, one aluminium and another silicon. These things have less negative charge than these things. These 2-to-1s have more negative charge, so they'll hold more cations. And how do you know which one you've got? These 2-to-1s, often these are the ones that will crack on drying and swell when they get wet. So if you've got clay soils that crack, they're these guys, and so they will have a lot more negative charge. And of course, this negative charge means that cations will stick to it. This is our nutrient retention, and that's why it's important. Sesquioxides can also have charge, and these are our iron oxides, and so I'm going to draw them in red. And they could be, you could have a sand particle that's covered with iron oxide, so red sands. So, it could be sesquioxide, or it could be that you had a clay particle originally and now you've got sesquioxide stuck around it, or it could be just a piece of sesquioxide that gradually gets bigger and bigger. And so these things are iron oxides, and they can have a charge also. But the thing with them is they have a pH variable charge, or variable charge with pH. And so they can be positive, neutral, or negative depending on pH. And as the pH increases, it goes that way. So as pH increases, we get more negative. So same deal, if this thing had a negative charge, cations would stick to it, and that would retain nutrients. Organic matter also has a variable charge as well, and so it can be neutral or it can be negative, and it becomes more negative as the pH increases. Okay, and so this at around about pH around about 5.6-ish, you'll have sort of half your organic matter having no charge and half having a negative charge. And as you increase the pH more and more, it becomes negatively charged. If you drop the pH below that, you'll get more and more of the organic matter not getting a charge. They're our clay components, and they have charge like that. I want you to remember that the charge due to sesquioxides and organic matter is variable, okay? It's not constant. This is constant. Okay, so they're our main players. So let's get into talking about the soil test. And a bit like the ABC, to sort of not show any bias towards any company, we're not going to mention any company, but we're going to use a soil test sheet that I've made up to talk through. And so we've got the good people at Dodgy Brothers Soil Co, where their motto is they hardly ever get it wrong. And so we've sent soil off to them. And of course, there are labs out there are many labs. You can test lots of stuff, but we want to be sending it to a lab where you are confident in the results that actually get done. And so what we need to make sure is that our lab, they're accredited, and that the key ones here are NATA and ASPAC. So ASPAC actually tests the accuracy of what's being done, what's being measured. And so if I was going to start a lab and I wanted to measure Colwell P, then I would get ASPAC accreditation for Colwell P. If I'm going to measure pH, I want ASPAC accreditation for pH. And so this is my guarantee that the numbers we're getting back are actually accurate. NATA, they test the process, and so how the samples are treated, the analyses that are done, how the wastes are removed, all that sort of stuff. So they kind of work, hand in glove a little bit, but this thing's the accuracy component. So you've got to make sure you have that for the things that you're getting tested. Now, good old Dodgy Brothers doesn't have that, but let's assume they did. So most soil tests have some component of information that you gave them when you sent the sample off, location, paddock, name. Importantly, soil depth, that's a really important thing. And this is all useful information in your records. I know on our farm, soil records, they were kept in an envelope, and there could have been various labs or whatever. That was our way of keeping our information. It was pretty poor in what could be done now with databases and spreadsheets, whatnot. So you've got information there. Then you've got the actual test itself. Now, some of the companies will provide some form of traffic light system. So out here, you'll have what's measured, the number that comes back. These will have the units in them. And then out here might have, and it could be, low, medium, and high, or it could be, red, yellow, green, or it could be adequate, or under or over. So anyway, there's some companies provide that sort of feedback, and I want you to think about where is that coming from, because some of this stuff matters where you are for a start, and so some of these numbers, depending on your location, could be a moderate value, but in another location, it's a high value. And in some cases, we need to understand how these boundaries get created. I'll talk about that in a minute. So just moving in, so soil colour, it's not necessarily just, I reckon the soil's brown. They use a Munsell colour book, which you would have seen. So it's just like a book that's got interior decorating colour cells for soil people. So it's all the colours of soil. But importantly, it comes up, marries it up with a word colour, so dusky red or weak red or whatever. And so whatever the colour is that the sample turned up in the lab, they will say this is what the colour is. And that's useful when you're communicating this to someone else that hasn't necessarily seen the soil. They can start adding things together, because the more brown the soil is, the higher the organic carbon should be. If it's a really red soil, then that sesquioxide, that iron oxide there might be more of that, and there'd be low organic matter. Soil texture, this is our physical measure of clay content. Okay, so it's not percent clay, but these terms are an estimate of percent clay. That in itself, by itself, isn't of use, but we end up using these texture as a surrogate for other things, and it might be pH buffering capacity. Certainly we can understand about water behaviour, like water retention in clays, for example, compared to a sand. So it's useful information. But obviously, if you've got more clay, then you should have more charge, because the clay is the stuff that's got the charge. And so if you've got a higher clay textured soil, you'd expect there to be a lot more cations held in the soil. Moving into pH. So pH is just a measure of acidity, negative log of the hydrogen ion concentration. What the negative number does mean is that as the hydrogen concentration increases, the pH will decrease. That's the negative bit. Now, this is the acid, right? Hydrogen ions are the acid bit. The log means it's a 10 times increase in concentration as you go from 7 to 6 to 5 to 4. I used to teach this stuff by just saying, look, the acidity that you've got at pH 6, you've got 10 times the acidity at pH 5, and you've got 100 times the acidity at pH 4. And I got through life like that fine, but I reckon we'd probably undersell that a little bit. So I think in pictures, which is useful and horrific all at once, depending on what the conversation's about. But if you thought about acidity as being like a bucket, and it could be like a bucket of acid, or it could, if you like, be a bucket of lime or a bucket of alkali that you have to add to neutralize this bucket of acid. So if that's a bucket of acid, you have to put a bucket of lime in of the same quantity to fill that up, right? Or the amount of alkali to fill that up. So at pH 6, if you've got one bucket of acid, at pH 5, you've actually got 10 buckets of acid. And so just to go from pH 6 to pH 5, you've got 10 times the acidity, but also means you've got to have 10 times the alkalinity to get you back to pH 6. And that gets a whole lot more horrific when you start looking at what pH 4 is, because it means that you've got 100 of these buckets, right? And then so if you filled up 90 of them, you get to pH 5. If you filled up 99 of them, you get back to pH 6. And so as you move south of pH 5, it starts getting more acidic. You're getting more and more of these acid buckets coming in. Like that log, it means that if you're at pH 4, you've got a hell of a lot of acidity that you need to work with. To me, this makes a lot more sense. I can kind of understand why it's so important to stay away from low numbers when you look at that. Anyway, so again, like I know you all know what pH is. To me, that makes sense, and I reckon I can explain that better to people, and they can understand why if you put on a ton of lime up here, you get a big change in pH, but if you put a ton of lime on here, you may not get much of a measure at all. And I've seen plenty of experiments like that, or field lime strips where they've done that. Oh, I put 2 tons of lime out and the pH didn't change much because you're just looking at that. Right, that's pH. Now, things like pH and electrical conductivity in the labs that I've been in anyway, this is done by taking 10 grams of soil, adding deionized water to it, stirring it, then measuring the electrical conductivity of that solution after it's settled. And of course, the higher the electrical conductivity, the more salt there is, but it's a 1 to 5 soil water extract. So 10 grams of soil, 50 mils of water. And whilst that's there, they stick a pH electrode in it, and that's what gets us our pH in water. And then they'll add a small volume of calcium chloride to that, and that ultimately the concentration of that will be 0.01 molar, which is roughly the same salt concentration or salt strength that topsoils have in them. And then they'll stick the electrode back in and measure pH, and that's your pH and calcium chloride. And so there's no right one or wrong one. They're just different measures of the same thing. But because this has got that extra salt in it, this pH is a lot more like what a plant actually sees, because plants don't grow in pure water. This will always be lower because our clays, which have negative charge, some of these cations will be hydrogen ions. And so when you stick that calcium chloride solution in, right, the calcium will come in here and kick that hydrogen ion off into solution, and it gets picked up by the electrode. So if you've got more hydrogen ions in solution, your pH has just gone down, which is why this pH in calcium chloride is always a lower number than what the water is. So it's just that you've had the calcium putting more of the hydrogen ions that were stuck on the clay back into solution. And so I talk about this negative charge for hydrogen ions and pH. It's like an interchange bench. So the hydrogen ions can sit on the clay. They're not in solution, so they don't get picked up by the electrode. When you move them, when you put cations in that make them exchange, they can go out into solution. If you had hydrogen ions out here making an acid soil and you put lime in and they take out the hydrogen ions, so lime increases pH, but hydrogen ions can come off the clay out into solution. And so even after that lime addition, the concentration of hydrogen ions hasn't changed, so the pH hasn't changed, even though you put lime on. And that's what buffering is. So pH buffering is driven by, in a lot of cases, things that have negative charge, because the hydrogen ions are sitting on the interchange bench waiting for them to be needed to come out in the solution. And of course, once you put on enough lime to remove all of them in solution and those on the interchange bench, that's when you get the big pH change. If you don't have a lot of negative charge, then you don't have a big interchange bench. A little bit of lime kills these hydrogen ions out here, and you don't have a lot to come and take their place. So a little bit of lime gets the pH change you want. We use this negative charge from the clays as a surrogate for pH buffering capacity. So that's complicated to measure. There's lots of different ways to try to do that, but it's easy to measure the negative charge in soil. So how we do that, and this is important because it's in the test sheet. So if you've got a clay and it's got a negative charge and it's got cations stuck on it, and there might be some calcium, and there might be some potassium, and there might be magnesium, and there's some hydrogen, and then there's an aluminium, and then there's more potassiums, right? So it's surrounded, cation swarm. If we want to know how much negative charge we have, which is what our CEC is, our cation exchange capacity, which is in layman's terms, how much negative charge is in my soil, right? Or the concentration of negative charge. We can't physically count these negative charges, but what we can do is we know that for every negative charge, there's a cation or a charge from the cation being satisfied. So we need to get all of these things off this clay and out into solution, and then we can measure the concentration of those in solution. And so in the soil test sheet, we have cations like potassium, calcium, magnesium, sodium, aluminium. So all these IUMs, they're all cations, calcium, magnesium, sodium. Anything with IUM at the end is a cation. So we're using ammonium acetate, and all that is, we're providing an ammonium cation in lots of numbers, lots of, right? And so there's heaps and heaps and heaps and heaps of these. And so they just come in and take the place of all of these, what we call native cations. And so they all go off into solution. And so after that magic's happened, you'll have a clay with ammoniums stuck around it. And out in solution here, you'll have all those native cations. And we just filter out that soil and then measure the concentration in solution of calcium, potassium, magnesium, sodium, right? And that's what we actually measure. So we add these things up, right? So we add up, this will ultimately get measured in parts per million, which is the same thing as milligrams per kilogram. And so we can convert that concentration into a concentration of charge by understanding what the molecular weight is of each of these things and its valency. Like, is it a 2 charge, 2 plus, or a 1 plus, right? So using the molecular weight and the valency, we can convert the concentration into the concentration of charge. And that's what centimoles of charge per kilogram is. Or in the old days, it was used to be called milliequivalents. This is concentration of charge. Now, why I think this is important, there's a couple of reasons. One is the unit is a positive, right? The centimoles, which is like centimeters, right? It's 100th of a mole, and a mole is just a number of thing, like it's an amount. So it's centimoles of positive charge. Why is it positive charge when it's really CEC is how much negative charge we have? It's because we're actually counting the negative charge by adding up all the positive cations that used to be stuck on the clay. And so that's why it's a positive. That's why it's a positive. So we get it by exchanging cations off with our extractant solution. Now, why that's important. Over here, we've got ammonium acetate. Now, the ammonium acetate method is buffered at a pH of 7. So ammonium acetate, so all of these cations, if you use ammonium acetate, is at pH 7, and in some methods they even use like pH 8.5, but 7 is the common one. Now, why they do that is because they understand that some clays have this pH variable charge, and so by buffering it at 7, it's keeping that variable charge constant at a constant place, right? So that's what that ammonium acetate does. So our ammonium acetate pH 7. So this is giving us our CEC. If we add up all of these cations that were measured in ammonium acetate, we'll get what we call our base CEC, or the sum of potassium, calcium, magnesium, and sodium. But it's at pH 7. For my mind, you want to know the CEC because it tells you the nutrient retention capability of your soil as you're managing it. And hardly, or certainly where I live, hardly anyone's got a pH of 7, right? We've got a lot more acid soil, so it's a lot less than that. And so the measured CEC at a buffered pH 7 is going to be higher than what you're trying to manage in the field. Very different story if you've got an alkaline clay, right? I understand that, and there are parts of Australia like that, and that's fine. But I'm just saying, if you've got a pH of 6, 5, 4, then this is giving you a CEC that you're never going to see in your management. And so what I use an ammonium chloride and a barium chloride extraction. And we use a book, right? Soil Chemical Methods, Raymond and Lyons, that's the Bible. And in that they have a bunch of tests, all the tests you can think of almost, and they have codes. And so I think that one is like 15E1, I think, from memory. The important thing with this is, so it's got ammonium and barium, and that does the same job as the ammonium did here in exchanging off the native cations. But importantly, it's at the natural pH of the soil. So whatever the CEC is of the soil that was sampled, that's what you're going to measure, because we didn't tool around and change the pH in our method of extraction. So that's what I use. The other thing about that is when you do that, you can also get aluminium out as well in the same extract for no extra cost, which is a win. Now, this one has aluminium extracted in potassium chloride, exactly the same deal. That potassium's what's kicking off all the aluminiums, so you can measure it, comes up in centimole. Add those things up. Now, if you add up the base cations, the potassium, calcium, magnesium, sodium, that's what we call the CEC, and it might be CECB for base. If you add aluminium to it, then, which is what in an acid soil, you get more aluminium, of course. And so they're taking up some of the bases that nutrients could otherwise have. And then it's also possible to measure the exchangeable acidity. And that, when you add up the aluminium and the exchangeable acidity, is the effective, what's known as effective cation exchange capacity, so the ECEC. Now, confessions of the soil person. I reckon this is the most bastardized thing we've done, because people, and I'm guilty of this, we'll add aluminium to these and just call it CEC, right? Because in our acid soil areas, that's what we end up with. We don't measure exchangeable acidity because it's quite difficult to do, and so it's an expensive thing to have. The justification, the rationale is that if you include it because it's taking up some of the space on the exchange sites, which is true, but we also get an idea of how bad acidity is by how low the pH is. So I'm not saying it's not needed. It's just another expense that I'm not. Yeah, personally, I can get through life without having it done, but I include aluminium with my base cations and use that as a surrogate ECEC. And in the New South Wales DPI soil acidity prime fact, where we've got a table of ECEC going down this way, and this is a table full of lime rates to hit certain pH targets, that ECEC is the sum of those. It doesn't include exchangeable acidity. So that's how that works. We take that number and we take our aluminium and we find out what percentage of this CEC is occupied by aluminium by simply just putting, in this case, 0.86 over the CEC, 6.18 times by 100, and that would be almost 14%. Okay, so ESP, the exchangeable sodium percentage, is just that number divided by the CEC. Calcium magnesium ratio, that number divided by that number. All of this is just calculated from this exchangeable cations. And so I think it's quite important that in a soil that doesn't exist at pH 7, that you actually find out what the CEC is at the pH that you're operating at, so you actually get a true measure of its nutrient holding ability. Right, I'm going to talk about phosphorus here as an example, right? So we've got plant available phosphorus, Colwell P. We use that in New South Wales. If you're Victorian, you'd know, you'd be probably more familiar with Olsen P. And so both of those things are soil, and it's like for Colwell, it's one gram, I know, into 100 mils of sodium bicarbonate, shaken for 16 hours, right? And I asked, why is it 16 hours? And the answer was because you can spend all day weighing out bloody soil into containers, squirt 100 mils of sodium bicarbonate into it, stick it on the shaker at 5 p.m., come back to work at 9 a.m., and guess how many hours you've done? 16. So that's why. So no chemical reason, it just fits in with a working day. And then Olsen is similar, except that it's 30 minutes, right, rather than 16 hours. And so, and the ratio is different. The ratio is 1 to 20, I think. This is a 1 to 100. I think Olsen is a 1 to 20. Now, what that means is that because you've got more time here, the number of Colwell P for any soil, the soil out the door here, if you'd had a Colwell P of 30, you would have an Olsen P of less than that, and roughly about half of that, so it might be about 15, right? Because this has had more time to react and actually drag phosphate off the surface where it's held, and it's held to the sesquioxides largely. So remembering back to our soil components, the iron oxides is what phosphate binds to, and not due to charge so much, but because it's iron oxide. So the more iron oxide you have, the more phosphate binding you get. Now we want to know about that, and we have that in our soil test as the PBI, Phosphorus Buffering Index. And what that is literally taking some soil, sticking it in a container with that same extractant solution that we used with the Colwell P, but giving it a spike of P. So a known amount of P goes into that for that same 16 hours, and then we can measure how much P is left in solution. Then we can work out how much P must be stuck onto the soil. The more P that gets bound up, the bigger this number. So phosphorus buffering indexes like 400, it sucks in a lot of P and gets bound up. So if you want to have P available for the plant, you'll need to put more P on. If you've got a low PBI, then more of the P that you add actually stays in solution and is able to be taken up by the plant. So that's what our PBI is. Now, people will say, that's fine, Jason, but is this an adequate number? Where does this fit in our low, medium, and high? Now, where that comes from is, and people will have rules of thumb or whatnot, but fundamentally where that all came from, we meaning the industry, over time, we did a bunch of trials, and in those trials we put fertilizer on, kilograms per hectare, and let's call it P, and you might go 0, 5, 10, 15, 20, 25 kilos of P, right? And then you have yield, tons per hectare here. And so at each one of these rates, you got a yield like that. So this is testing our response of P addition to our yield. There it is. And so you do that on a bunch of different seasons, different soils, different locations, different crops even. But from this, you take three pieces of data. One is you take the maximum yield. So this is yield max. And then you take the yield where you put nothing on. And this is called yield 0. And so if you have your yield 0 divided by yield max times 100, this is our relative yield, okay? And so you've got that, and then you've got the soil test value at 0 rate. So we've got this, and we've got this. We've got those two pieces of data for every trial around. So then our x-axis here will be our soil test value. And so this might be, in this example, Colwell P, parts per million. Okay, so this might be, well, it might be 0, 10, 20, 30, 40, 50. And on our y-axis, we have relative yield, percent, 100, 50, well, 50 would be here. Okay, and then you plot all of the trial data on here. So we've got trials from all over the place, different years, different results. There they are. And then we draw a line of best fit through that. And then we can say, okay, what's the point where you get, say, 95% relative yield? It's here. Then this is our critical value. Critical value. Okay, so a lot of people go, right, this is the number I've got to have to get, maximize yield in terms of P. This curve normally has a really steep bit, a kind of a plateauing flat bit, and then a really flat bit. Okay, so here's our low, medium, and high that you often see on the traffic light system. Okay, and so this is for Colwell P, but it's for, you can have it for anything that you measure, right? So fundamentally, that's the process, the concept that goes into creating what is the critical value, so that when you get a number on a soil test, you have an idea of, is it good, bad, or otherwise? Do I need to add? Do I need to worry about it? So this is really important. And so if you're working with a company that gives you the traffic light system, fine. You probably need to create some confidence yourself, whether it works for you or not. We are so fortunate to have the better fertilizer decisions for cropping. So www.bfdc.com.au. And what it is a database of basically all our Australian trial data that we could get. And so it literally has, like, I think it's 5,000 or 6,000 trials in it. And I've just got here, so you can put in your soil type, you could say what you're measuring, in this case it's Colwell P, you can fool around and play around with growing season, location, there's a map here, you can even circle bits whereabouts in the country you want to be, and then it will show you the data for the relative yield versus soil test value for the trials that are relevant to what you've selected. So this what you see here is all of the dry season cropping in New South Wales for all crops. So a lot of these are actually wheat, right? And there's some canola there. There's like 6 lupin trials, right? This is it. 6 lupin trials. And so there's people making recommendations on how much P you need to put out for lupins based on 6. It looks a lot better in color, granted, but here's our curve, and you can see the variations. It's not a definite point. This critical value is not a definite point. They give you ranges here for various percent, how far up this relative yield you want to travel, and I give you the critical value somewhere in this range, right? And so you can do that. You can use this for your area, your crop, and see what it should be. And you can do that for sulfur, potassium, nitrogen, and phosphorus with that database. Fantastic. Love it. Right. So they're our critical values. So we have that for P, and we have that in some cases for N and S and potassium. So once we get away from that, you really have to ask, where's the information coming from? Some of the companies may have their own trial data, that's fine, but it's a fair question. And so I know people are often interested in this calcium magnesium ratio. And so from what we've seen in trial data, anywhere between 2 and 20 are happy days for most agriculture. Once you get below 2, you have some soil structural problems. Once you get over 20, you have some magnesium deficiency problems, but that's a broad range. And I'll just point out too, and I know a lot of people are aware of this, but if you're interested in that paper by Peter and Neil, fantastic. It used historic data from America, basically, where this concept of this ideal ratio came from. They actually used their own data, that the original author's data, to show that there's no ideal ratio. So that's in the Soil Science Society of America journal in 2007. Something like this critical value, where we're using ultimately to work out from a soil test, do I need to add something, or am I in a sensible range? They're all based on these curves. The depth that this soil was taken at matters, okay? And in most cases, historically, it's like 0 to 10, because that's what a lot of trial data is in. But I'm concerned personally that a lot of these trials that were in that Better Fertilizer database, some of those came, like the first ones were in 1958, and they go right through to now. But there's a lot of old stuff in there. And so sometimes the tillage system matters. So how much cultivation went on, how much mixing, because now we have no till, we're not having the mixing anymore. And I just want to show you this. This is a Colwell P via depth. Okay, and so 0 to 10, this had a Colwell P of 60, which is high, right? It's adequate, it's good. But in reality, after 5 centimeters, the Colwell P was just over 20, which would be low. And so we know this because that's how we sampled on these trial sites. And when you look at this, it's got a cation exchange capacity that's really high in the surface, and it has high organic carbon in the surface. So this organic carbon, because organic matter has a charge, it can be negative at high pHs, right? So we're getting this negative charge from the organic matter. And so this was actually feedlot manure put out, which is why there's so much Colwell P. But my point is that if you sowed a seed at 5 centimeters, you're going to be P deficient, even though your soil test said that you were fine. And I think that's the concern. So I think we need to think about what we're doing to the soil fertilizer-wise on top, and where we're placing the seed and what the Colwell P is, because P doesn't move, it's not a mobile nutrient. And so I actually think we're under fertilizing a lot of our soil because of this P stratification. I've seen it time and time again, that curve is real. It may not be that high, sometimes it's down here like that, but it's real, where you don't have cultivation going on. So we could be under fertilizing a lot, I think, my opinion. Now, this cation exchange capacity, clearly, I hope you know it's important because it holds cation nutrients against leaching losses. You can't, or it's hard to, change clay content. Some of the Victorians do it, South Australians do it, Western Australians do it, where you bring clay up from beneath. There are a lot of parts of New South Wales that would not be a good idea, champion, but you can change organic matter content. Our management of pastures especially can increase soil carbon, and when you increase soil carbon, you increase the cation exchange capacity in the topsoil, which gives you a fertility benefit. And of course, throw into that, if you actually increase your pH, so stop being satisfied with having acid soils, as you increase the pH, more and more of that organic matter is having a negative charge, contributing to a nutrient benefit to your system, which is a win. So on that then, hopefully you feel like, in summary, that we've got maybe a better understanding of what's in the test, what's tested in terms of, say CEC actually extracting cations off and how that's done and at what pH it's done. We have just remembered where critical values come from. Okay, so it's those response curves, and so often that critical value is not a really super duper defined point, it's just an indication. And we have, using that database, we have in some cases really good clarity on what it should be, in others we don't have so much. And just again raising that idea that because we don't mix our soil anymore, our 0 to 10 samples coming back could actually be giving us an inflated idea of what the plant would see if we're sowing our seed deeper into an area that has lower P. It may be under fertilized. With depth, we need to consider depth more. So our 0 to 10 is fine for monitoring things like Colwell P and maybe pH, and maybe, I say maybe because those of you who heard me talk before, I think we need to be going down to at least 20 and in 5 centimeter intervals is what I would do if I was me, and so that monitoring works for that. But things that move, so sulfate and nitrate, then deeper matters. Okay, so 60 centimeters is the depth that you'll be needing to go to, or more, depending on what you're trying to achieve. If you've got a problem, you're chasing a problem, the plant is the best indicator of what it experiences. So if you've got roots that go down and then just stop at, say, 50 centimeters, then this is the area where we need to be taking our soil sample to find out what the problem is. It could be, maybe it's salt, maybe it's an EC thing, maybe it's sodicity, ESP, maybe it's pH, it's really acid or really alkali. But that's the bit you need to look for. So dig holes, see what the roots are doing. Where there are problems, go looking. All of the stuff that we spoke about were chemical, and so far in the 0 to 10 centimeters. And often the type of thing that brings you unstuck in terms of roots getting in will be a chemical but physical issue, and they occur deeper. So we need to go looking, we need to sample deeper if you're trying to diagnose a problem. And it's not blindly going, we'll take 0 to 10 and we'll do it in 20 centimeter intervals. Look at the plants and see what they're doing, see where they're stopping, and use that to identify where you need to go and take your sample from. So I'm going to leave it there, but hopefully some of that was useful. Hopefully some of that explanation was useful. The thing I didn't talk about carbon. It's measured by combustion at ridiculously high temperatures, and we actually measure the gases that come out of it. And because we do it that way, we can measure nitrogen, carbon, and sulfur all at once from that organic matter. Rightio, Luke, back to you.